Swayam Prabha. Digital India. Educated India.
Earlier, we have subdivided or classified the whole range of materials in terms of electrical properties in different subgroups. Some of them are conductors, some of them are semiconductors, superconductors, and there are a group of materials which are called insulators. It is expected that the electrical conductivity in these insulators is very low, or in other words, the electrical resistivity is very high. We have seen earlier that the electrical resistance is orders of magnitude larger than that of metals or semiconductors. But when we apply some electric field, we are putting in some energy, and therefore, the materials are supposed to respond to this electric field. So, today's topic is what happens when you apply electric field across a insulating material having a very high electrical resistance. Obviously, there is no possibility of long range charge transport. We do not get appreciable amount of current flowing through the material. That means, the charge species are not moving over a longer distance. However, these charge species do respond to an applied field, and let us see what exactly happens. Basically, the charge species moves within the material over a small distance, not the large distance or across the material what happens in a conductor. So, there is no long range charge transport, there is no long range movement of the charge species. However, there is a short range movement, may be limited to the interatomic spacings. So, within the interatomic spacing there is a movement of the charge species, but they do not break their bonds with the ion cores. However, they change their positions, and that is how some of the energy get stored in this material. So, the insulators are basically form capacitors, okay. And if we look at the basic phenomena, what happens in an insulator when we apply electric field, or in other words, sometimes they are called dielectric materials. There is a dielectric phenomena which takes place, and that is what we want to discuss here. The materials used to insulate, but in general since they have a very high resistance, they insulate from a conductor. So, if a particular conductor has to be insulated from another conductor or from its environment, these insulators act as an insulating barrier. So, materials used to insulate an electric field from its surroundings are required in a large number of electrical as well as electronic devices. So, in addition to the dielectric properties, just simple insulation is also important, and whenever we are using a semiconductor device or a conducting materials to insulate it from its surroundings, a insulating material is quite useful, and that is another function of an insulator. The electrical insulator obviously must have a very low conductivity, as I mentioned just now, or very high resistivity to prevent the flow of current. So, there is no flow of current. Ideally, a insulator should have a zero current or infinite resistance, but in reality there is always a finite amount of current flows through it. Sometimes it is called leakage current, and that can be measured also. with different kind of instruments. The examples of some of these insulators we have seen earlier, once again can be repeated here. The porcelain basic insulators, clay based insulators or clay based ceramics, aluminum oxide, alumina, cordierite is another important insulating ceramics. Mica is a natural mineral and also one of the ceramics, that is the layered kind of ceramics, and some glasses. Glasses of different compositions, some glasses of course fairly conducting, whereas most of these glasses are insulators. And of course, there is a range of plastics or polymers which are in general insulators, but maybe you are aware that there are examples of plastics or polymers which are also conducting in nature. So, we are talking about basically different kind of insulators, and one of the best way to understand what happens when an insulator is under an electric field is to look at a capacitance or capacitor. Okay. Capacitor is a very simple device where you have two metal electrodes, one is positively charged and is negatively charged, and in between you have a gap, and that gap may be filled up with an insulator. Okay. Even air is a good insulator, fairly good insulator. So, between the metal, between the two metals, if there is an insulator, that can be called as a capacitor, and we have some important parameters of this device as well as the materials. So, here is an example of a what we call a parallel plate capacitor. It is as the diagram shows that we have a positively charged conducting plate, on the other side negatively charged conducting plate, and the gap is about d, spacing is d, and the area is A. We apply a voltage V across this two electrodes, and the charge which can be stored. Okay. Charge is not flowing away, the charge can be basically stored. The total amount of charge stored is equal to C into V. C is the capacitance of that system or device, and the V is the applied voltage. This gives rise to a few more equations like V equal to Q by C, and that is equal to integration I dt by C, because charge is nothing but the accumulation of total this is the total charge over a period of time flowing in the form of a current. So, the total current flow over a period of time gives you the total charge which is accumulated or flown across the two electrodes, and C is the capacitance of that. It is a device parameter, and it is has some unit which we will discuss in a few minutes. It also gives rise to another equation in terms of I, the current flowing through the capacitance, okay, or capacitor. Although we say is an insulator, but there is a current sets up within the material. It is not flowing across the material, but there is some current flowing because charge is getting accumulated, and therefore, flow of charge is nothing but the current. So, that current is given by I equal to C dV dt, the derivative of voltage with respect to time. In fact, we will look into another situation. There are two pictures here. One is the same thing what we have shown earlier. It is in between we have a free space, one is positively charged plate, another is negatively charged plate, and in between we do not have any material. Here it is evacuated. So, vacuum or free space. So, that also give rise to some kind of a capacitance value and charge accumulation. However, on the right you have a material, you have a solid is basically an insulator. If it is a conductor, then charge will be flowing from one electrode to the other. So, we are not, a conductor cannot be used obviously for charge accumulation or forming a capacitor. Therefore, we have a insulating material, in other words it is called a dielectric material. So, all the insulators have a dielectric phenomena, and that is what we are going to discuss here. So, there is an accumulation of charge, but there is a redistribution of charge. Okay. So, whenever there is a material insulating material, some changes do take place within the charge distribution, or so far as the charge distribution within the volume of the material is concerned, and how it is done, that will be discussed. So, initially we have one situation where there is a vacuum. Vacuum being a good insulator, certain amount of charge can be also be stored when two conductor plates are kept in vacuum, that is shown in A. However, when a dielectric is placed, that vacuum is replaced by some kind of insulator, an additional amount of charge can be stored due to better polarizability of the dielectric. The term polarizability will explain in a few moments. So, there is a difference between a vacuum situation where is a vacuum in between the two electrodes, and there is a insulator or a dielectric medium, we call it dielectric medium. So, there is more effective charge accumulation or energy storing capability whenever there is a good insulator. So, that is what has been shown here. We can see some more equations like this, the same for the vacuum. Whatever equation we have written earlier is C0, the capacitance. Capacitance is a geometric function. So, it is A by D, A is the area, D is the distance, and we introduce a term called epsilon naught, epsilon 0 multiplied by A by D, that is the capacitance of this simple device. So, if you have a vacuum, then vacuum has some kind of insulating property, and that is characterized, or the dielectric property is characterized by epsilon 0, which is known as the permittivity of the free space. Okay. It is a constant, and we will come across this particular term repeatedly during our discussion. However, if we have a insulator, as you have shown earlier picture, C changes to capacitance with the insulating material in place. So, C0 epsilon prime by epsilon naught. So, epsilon naught once again is the permittivity, dielectric permittivity of the free space, and it is a constant, and C0 has been defined earlier in the above equation, in the previous equation, and so C0 multiplied by epsilon naught by epsilon prime by epsilon naught, where epsilon prime is the permittivity, dielectric permittivity of the material which you have placed, which replaces the vacuum. So, you have a overall capacitance with the insulator in place is C0, C0 has been defined above, and K prime. K prime is the relative permittivity, or in other words K prime is equal to the epsilon prime by epsilon naught, and it is sometimes also represented as epsilon r. The relative permittivity, or K prime, when we write K prime, is also called the dielectric constant. So, dielectric constant K prime, in some places one can see also only K, but K prime is a better representation, that will be clear when we discuss later why we are using K prime. But in many literature you will also find K, just K as the dielectric constant, and epsilon r is the relative permittivity, which are basically the same quantity. This dielectric constant is a material parameter, and it does not depend on its shape and size of the material, but it depends on the structure of the material, the composition of the material, and the particular type of bonding, chemical bonding it has. So, K is a material parameter of very importance, and that is how one can characterize a dielectric material. So, once somebody wants to design a capacitor, a particular value and charge storing capacity of a particular system or device, K prime or K, dielectric constant of the material, is of very utmost importance or prime importance, so that one can design precisely what kind of capacitors can be fabricated out of them. These are just the definitions of the different parameters used here. Epsilon 0 is the dielectric permittivity of free space vacuum, epsilon prime is the dielectric permittivity of the insulator, and K prime is the relative permittivity, dielectric permittivity or the dielectric constant of the insulator. So, it is also the same as epsilon r. K prime and epsilon r are actually the same quantity, they have been used in different context. Few important equations once again and some of the units. Okay. Capacitance is just what have been indicated, epsilon r epsilon naught A by d is the geometric factor of the capacitance, and Q, the charge accumulation, is epsilon r epsilon naught A v by d, because basically Q equal to C v. Okay. So, this part is C and this part C v, and so that once again the same equation has been written here. Now, the units, units of charge is known, is nothing but coulomb, and capacitance is farad. Okay. V is the potential difference in volt, small d is the separation or the thickness of the insulator, and it is in meter. Epsilon naught, which is a constant term, and it is the permittivity of the vacuum or sometimes called permittivity of the free space, and the value is 8.854 into 10 to the minus 12 coulomb square per meter square or farad per meter. So, farad per meter is a more common unit which is used, and epsilon r, the dielectric constant, is nothing but it is a relative number and it does not have any unit. Next, we look at what exactly happens in an atomistic scale when we apply an electric field against an insulator. So, a dielectric material responds to an electric field differently than the free space because it is constituted of charged species. Okay. Free space does not have a charged species, so the permittivity is much less. Okay. So, and therefore, when you apply a electric field against an insulator which is having a charged species, some of these charged species may be displaced to a limited extent, thus neutralize a part of the applied electric field. So, as I mentioned earlier, whenever we apply a field, electric field or an energy, the material or the internal structure of the material, internal constituents of the material respond in a particular manner. Okay. In case of conductor, the free electrons or the free charge carriers moves over a larger distance from one end of the solid to the another, or one end of the medium to the another medium, another end of the medium, whereas in an insulator, because they cannot move over a large distance, and that is the property of an insulator. So, they move to a very limited extent. Okay. So, they do change their position, geometric position but in a very limited extent, and that is the characteristics of a particular material and the particular structure, particular chemical bond it has, and so on and so forth. So, once again we can have this kind of there are more or less the same equations has been written slightly differently. So, starting with V equal to Q by C and C equal to K prime C 0. C 0 is the capacitance of a vacuum of a particular geometric configuration. These two gives rise to these two equations give rise to another equation, which is V equal to Q by K prime, Q over K prime by C naught, okay, or C 0. So, you have basically a ratio of Q by K naught to C 0. C 0 is the capacitance of the vacuum. So, it indicates that only a fraction of the charge known as the free charge, which is Q by K prime. So, this is K prime is a number. So, Q prime is some fraction of Q sets up the voltage across the electrodes, and rest of the charge known as the bound charge is neutralized by the polarization of the dielectric material. So, there are two different forms of charge or two different kind of situation happens simultaneously, of course, and one forms the bound charge and there is free charge. So, free charge which is about Q by K sets up the voltage across the capacitor, whereas the bound charge actually does some internal rearrangement of the charges, okay, and neutralize and gets neutralized by that process. So, this can be shown here, bound and free charges. This is two parallel plates or the electrodes, these are conductors, one at the top, one at the bottom, and we are applying a negative charge or negative potential, negative potential on the top and the positive potential on the bottom electrodes. So, these are the charges available within the insulators, okay, within the in between the two electrodes we have some charges already present in the material. They get reorganized when we apply electric field. So, we have two types of charges, one is with the square, all are negative charges of course, but one is a square and another is circled. Okay. Here also all of them are positive charges because it is connected with the positive potential. So, you have two different kind of charges, one is encircled by a square and is circle. Okay. Now, you can see here these positive charges has a corresponding negative charge inside the material, and then that is neutralized by another positive charge. So, there is a realignment of the charges against this positive and negative charge. Okay. So, you have whatever positive and negative charges were present either in the form of cations, anions, or maybe the electrons as well as protons. So, all of them will realign themselves against the electric field and some of them will be neutralized. So, these are the bound charges. So, these charges inside, whatever charges inside the material is, they will bind some charges on the surface of the electrodes. So, on this side the negative charge will be bind by this positive charge, and on this side this negative charge will bind this positive charge. Okay. So, that way there will be realignment of positive and negative charges, and each of them actually forms a dipole. So, these are formation of dipoles, that means a positive and negative charge separated by a distance. So, these are as a result of the application of the electric field, you are generating some dipoles within the insulator, and these dipoles are binding some charges on the surface of the electrodes. However, all the charges available on the surface of the electrodes are not bound by the dipoles created or generated within the solid. Only a fraction of them will be bound and others will remain free, and that is what it is shown here in the same diagram. These are free charges, circled ones are free charges, there is no corresponding dipoles on this side. So, these are free charges which actually develops the voltage on the plate, the metal plates, metal electrodes, and these are the changes which takes place within the solid. So, we have two types of charges on the surface of the plate, one is the bound charge and there is a free charge. So, that is what has been described earlier. It indicates that only a fraction of the charge known as the free charge, which is given by this, sets up the voltage across the electrodes. Rest of the charge known as the bound charge is neutralized by the polarization of the dielectric material. So, this is what we call basically the polarization, that means creation of some dipoles within the material. Initially, we will find later on that these charges might not be forming dipoles or they are not bound to each other. So, they are more randomly distributed. Of course, in a crystal there are certain amount of periodicity, but they might not be aligned to this. So, this alignment and formation of the dipoles, actually the phenomena is called the polarization. So, when you apply an electric field against a insulator, the charges gets polarized and that polarization is what we call the dielectric polarization. So, this is an important phenomena of a dielectric material. So, polarization is a very common phenomena and very important phenomena whenever we are talking about a dielectric material and it is electric field is applied against it. So, polarization and flux density, displacement of charged species in a dielectric material results in creation of electric dipoles. That is what has been discussed, which in turn enhances the flux density. So, it is called the dielectric flux density. Both are the consequences of dielectric polarization. So, they are related in the following manner. So, we have two terms, one is the polarization term and there is the dielectric displacement or flux density. Okay. So, these are the two terms, how they are related. D, the displacement or the flux density is equal to epsilon naught, again the permittivity of the free space comes in multiplied by the electric field not the voltage or the electric field, plus polarization. Okay. P is called the polarization. So, dielectric displacement or the flux density is equal to epsilon naught E plus polarization, and that is all nothing but epsilon prime multiplied by E. So, actually dielectric displacement is D equal to epsilon prime multiplied by E, and this is again equal to epsilon naught into E plus P. Okay. P is the polarization. So, this is the one can see this is the polarization of the free space and this is the polarization of the insulating phase or the dielectric material in between. So, this is the relationship between the two parameters. We will also have a relationship because polarization is the result of creation of dipole moments within the material. The polarization P is also defined as the total quantity of dipole moment generated per unit volume of the material. Okay. So, that is the polarization. P is equal to N multiplied by mu. N is the number of dipoles generated per unit volume and mu is the dipole moment, the moment of each dipole. Mu is also given by Q into D, where Q is the pair of charge, that means one is a positive charge and there is a negative charge with the same magnitude. So, plus Q and minus Q separated by a distance D gives you the dipole moment Q into D. Okay. So, that is the dipole moment mu, and how many dipoles are created? How many dipoles are created and what is their moment, dipole moment, and what is the total number of dipole moment? N is the total number of dipoles generated per unit volume. So, per unit volume, whatever the total number of dipoles, the dipole moment generated, that is the measure of polarization. So, higher is the dipole moment creation, higher is the polarization, higher is the moment dipole moment for each of the pairs, that also create more dipoles. So, if Q increases, P increases, if D increases, also P increases, and if N increases or N is more, P is also more. That means, how many dipoles are getting generated. There is also another parameter used in dielectric literature, that is dielectric susceptibility. From an earlier relationship, these are rearrangement of those equations earlier used, P equal to epsilon prime E minus epsilon naught into E. So, P is actually the parameter related to the insulator or the dielectric material. So, this is the total effect, that is the epsilon prime into E, subtract from that about the so called the vacuum. So, if you subtract the magnitude or the quantity of the polarization from the vacuum, that from the overall polarization, that is actually the polarization of the solid. So, that can also be written in this form, epsilon prime minus epsilon naught into E, and since there is a relationship between this and K. So, if you it can be written as epsilon prime within bracket K prime minus 1 into E. So, this is what we can know by rearranging the earlier relationships we have used. So, the dielectric susceptibility, actually it is chi, it is not x, it is chi, is defined as the ratio of the polarization to the electric field. It is also the ratio of the bound charge density to the free charge density. Okay. So, chi is actually we have discussed few minutes back about the bound charge and the free charge. So, that ratio is also actually the dielectric susceptibility, another parameter used in dielectric literature. So, chi is again defined by polarization total P by epsilon naught E. Okay. So, this is for the vacuum, this is for the vacuum and this is for the material. So, P by epsilon prime E equal to actually K prime minus 1. So, it is the dielectric constant, minus 1 is just the dielectric susceptibility. So, there is a very simple relationship between the dielectric susceptibility and the dielectric constant. So, it is the 1 less than the dielectric constant or relative dielectric constant. Now, there is also a concept of local field, local electric field experienced by the charged species within a dielectric is different from that of the external electric field applied from the outside due to the polarization of the species surrounding any particular species. Okay. What if we want to find out what is the electric field experienced by this particular charge species when electric field E is applied from outside. So, this is once again a parallel plate capacitors these are the two electrodes, one is positively charged, another is negatively charged, and we are applying a field E. Now, this inside the material, a particular charge species, what it is experiencing is not exactly equal to the E, it is actually E prime, which is slightly different from what we measure from outside. So, that also have to be considered while you are talking about what is happening inside the material. So, that is what is called the local field. Local field is different than what we apply from outside, and that is because all these things are dipoles. Okay. Dipoles have already been generated and they have create some internal field in addition to the external field. So, the external field generates these dipoles, and these dipoles has an influence on the neighboring dipoles or neighboring charge. So, as a result, at a particular point any charge species experienced or the field experienced by this charge species is different from what we apply from outside. So, when we are trying to calculate what is the polarizability and what will be the dipole moment and so on, one has to take care of this kind of situation. We are not going to the details of the calculation, but only it will be convenient to know that this electric field is different from that applied from the outside, and that is called the local electric field E prime. Normally it is called E prime, which is different from E. Okay. So, that is another situation one has to keep in mind. With this in mind, if we want to find out another parameter which is called polarizability, that is the ability of the material to get polarized. So, that is what we call the polarizability, and that is defined in this manner: the average dipole moment, which is mu bar of the elementary particle would be is proportional to the local field. Okay. So, the average dipole moment mu bar of the elementary particle or the elementary dipole is proportional to the local field, okay, E prime, which we have just discussed, and the proportionality constant is known as the polarizability or the alpha. Okay. I think there should be, change it. This should be elementary dipole. Right, is proportional to the local field E prime, and the proportionality constant is known as the polarizability with a parameter like alpha. So, mu bar is proportional to the E prime, not E. That is the only thing one has to remember. It is not E. E is the external field normally applied, and E prime is the internal field or the local field experienced by this particular element or dipole. Okay. So, and the proportionality constant is the polarizability, and it gives an idea how easily or difficult it will be to polarize a particular material. So, it is once again a material parameter. And in terms of the polarizability, the overall polarization may be expressed as P equal to n alpha E prime. So, once again it is the polarization total dipole moment. So, this is the dipole moment for each elementary dipole, and these are the number of dipoles per unit volume. So, once again In another way, P can be expressed in terms of the polarizability, another material parameter of any particular material. Well, with this phenomenological description of what happens when we apply an electric field against an insulator, what happens, what kind of dipoles created. Basically, there is a polarization, the more number of dipoles are created, and that dipole gives rise to dipole moment, and the polarization is basically a measure of how much dipole moment is generated per unit volume. Okay. So, ultimately when we apply an electric field to an insulator, instead of a large range conduction, long range conduction or long range movement of the charge carriers, there is formation of a dipoles. So, some amount of reorientation of the charge distribution, redistribution of the charges takes place inside the material, and that absorbs the energy. Okay. That absorbs the energy, and therefore, the energy, electrical energy gets stored inside a capacitor or within a dielectric material. Now, there are different mechanisms by which these dipoles can be generated. Okay. Dipoles, as you can understand, it is nothing but two charges, one positive charge and another negative charge, separated by a distance, and that distance is that has to be separation. So, the center of positive charge and the center of negative charge must not coincide. So, initially in a solid or a liquid, the center of positive charge and the center of negative charge normally coincides, and therefore, there is no net distance of separation. So, dipole moment is 0, that is the normal concept. But when you apply an electric field, there is a distance of separation, the net distance of separation, the center of positive charge and the center of negative charge distribution throughout the material gets separated, and you form a dipole, and that is what has been given here. There are 4 different mechanisms, distinct mechanisms by which there is a distance of a dipoles can be generated. Okay. This is the first one is called electronic polarization, second one is called atomic polarization, third one is called orientation polarization, and the fourth one is called space charge polarization. So, let us see what exactly mean by this terminologies. On the left, we have a situation when there is no field. So, it is an equilibrium situation, there is no field is applied. On the right, the situation when a field is applied. Now, in this you can see there is a electron within electronic. When you are considering electronic polarization, we are focusing our attention with a to each individual atoms. Each atom has a positive core or a nucleus around which there is a electron cloud. Okay. There is electron cloud, large number of electron clouds are moving around the positive core. Okay. So, that is the ion core, and around that is the electron cloud. So, this is negatively charged and this one is positively, center is the positively charged. So, center of the negative charge here, because of the uniform distribution, symmetrical distribution, is also at the core of the atom, where there is a positive charge. So, there is a net distance of separation is nil, there is no net distance of separation. So, there is no dipole moment generated, although there is a positive charge and negative charge, but D is 0. So, when we are talking about Q into D, D is 0, therefore, there is no polarization. So, it is a unpolarized situation, okay, unpolarized situation of the atom. But when we apply an electric field, this is the direction of the field, there is a separation. That means, the electron cloud is no longer spherically symmetric, but it becomes ellipsoidal. Okay. Once become ellipsoidal, the center of negative charge is here and the positive charge is here, and therefore, there is a net distance of separation. And so, just by applying electric field, there is a redistribution of the charge, and therefore, you will get a dipole moment, and the particular atom gets polarized. So, that is happening in the atomic level within each atom. Each of these atoms will have a electronic polarization sets in when an electric field is applied. Next is atomic polarization. Now, in this case we are talking about two different atoms, not electrons. These are two different atoms. Okay. So, there is a bond, chemical bond between this atom and this atom. The spring represents some kind of bond. So, they are not free, they are not completely free, they have some kind of binding energy or binding force, and that spring represents that. Okay. So, initially this is the distance of separation. Okay. Unlike here, the distance of separation 0, here there is a distance of separation, because one cation, for example, one cation is located next to one anion, but there is a distance of separation or interatomic spacing. So, these are actually interatomic spacings which is shown here, and the spring is represents some kind of bond or some kind of binding force between the two. So, there is a, if you are just considering this set of negative and positive ion, there is a polarization. However, when you are talking about the whole solid, these moments will cancel each other, because they are distributed in a random fashion, and there is not only random fashion, there are systematic fashion. So, that the overall dielectric moment or dipole moment is 0. So, one is positive, one is directed in this direction, maybe the next one will be directed in the opposite direction, and as a result the whole solid will have a net 0 dielectric moment or dipole moment. However, when you apply electric field, just like here, there the spin is elongated or extended. So, the distance of separation between these two and the distance of separation between these two in this condition is not same, this may be little higher than this. So, as a result there will be again a net dipole moment. So, there will be increase in dipole moment in this situation compared to that situation. So, that is also give rise to polarization. So, this is a atomic polarization, or sometimes also called ionic polarization, because if there are ions, actually it happens between the ions. This is one, this is an anion and this is a cation. So, it is more of an ionic polarization, but it is taking place in the atomic level, a pair of atomic level. Then there is another third kind of polarization, what we call a orientation polarization. This is a very special case in some materials, not in all materials. In some of the materials there is already a dipole moment present. Okay. We will see a group of materials called ferroelectric materials, where just like ferromagnetic materials you have magnetic dipoles. Here in ferroelectric materials you have electric dipoles already present because of certain crystallographic consideration or crystallographic nature of that particular structure. So, in such cases you have, just like a ferromagnetic material, you have a dipole moments present already. Okay. Some dipole moments are already present, but they are randomly distributed. Okay. Here they are in a random fashion directed in different directions, and therefore, the net dipole moment of the overall solid is 0 here. However, when you apply an electric field, they try to align themselves, because they have a dipole moment, they have a particular direction in which they want to remain, and if you apply an electric field from outside, they actually try to align themselves along the field directions. May not all of them All of them may not completely align, they may not come parallel to each other, but depending on the applied electric field they will tend to come parallel to the electric field. So, consequently there will be change in the overall dipole moment. So, this from a 0 dipole moment situation, because of the randomness, you have 0 dipole moment, overall dipole moment of the solid is 0, whereas in this case because of the realignment there will be a net dipole moment. So, that is also another way the material can get polarized or respond to an applied electric field. So, this is the third kind of, that is why, because it involves only a reorientation of the dipole moment, it is called orientation polarization. The fourth one, the last one, is space charge polarization. This is very similar to an electrochemical system. Okay. The polarization which happens in an electrochemical system. Electrochemical system, you have an electrolyte and the electrode, and there is an interface. So, in any electrochemical system there is a charge transport through the electrolyte, and then the charge gets neutralized at the interface of the electrode electrolyte interface. Okay. So, and if this interfacial reaction is not fast enough compared to the volume movement of the charge within the electrolyte, then there may be a charge accumulation at the surface, at the in fact at the interface of the electrolyte electrode electrolyte interface. In fact, we have seen that here also more or less when you are talking about a capacitor, the parallel plate capacitors which we have discussed earlier, it is basically analogous to an electrochemical system where the electrolyte is the dielectric and the electrode is the parallel plate conductor conductor plates. So, there may be accumulation because there is small range, small length or short range movement of the ions. So, there may be a rearrangement of ions at the interface. If this may be the interface, this is one. Here you can see both negative and positively charged charges are distributed more or less randomly. So, there is no net accumulation of charge, or net dipole moment is 0 once again in this case, but because of the short range orders, or sometimes there may be a long range order, not short range order, short range movement. You can see here after the application of the electric field, the negative charges goes towards right and the positive charges tend to go towards the left. And because of the interface there, they are not getting fully neutralized with the electrodes placed here, and therefore, more number of positive charge gets accumulated on this surface and more number of negative charges gets accumulated on the other surface. So, instead of a complete random distribution, you have a preferred distribution. On one side the positive charges moves in one direction and the negative charge moves in the other direction, and they gets accumulated on the surface or the interface, and that also give rise to a total or increase in dipole moment and therefore a polarization. Okay. So, this is the last kind of polarization mechanisms. So, you have 4 different kind of mechanisms by which the material can get polarized, or creation of dipole moments or increase in dipole moment. Okay. That is what can happen. In fact, there is another in a continuation with these mechanisms, here these 4 has been subdivided into actually 6. Well, we have once again these are mechanisms. The electronic mechanisms does not have any subclassification, atomic or ionic that also do not have any subclassification, but the other 2, this is orientation polarization and the interfacial polarization, has 2 different subgroups. One is high frequency and there is low frequency. Okay. So, high frequency dipolar or orientation present in normally ferroelectrics as I mentioned earlier, and low frequency dipole are present in linear dielectrics or sometimes in glasses. So, there is a sub classification of this orientation polarization. So, in both these cases there is already a permanent dipole moments present, but they are of different nature, and so there is a sub classification here. So, these two are actually two subgroups of orientation polarization, and similarly the last one, the space charge polarization, also have two different subgroups. One is called interfacial space charge at electrodes as mentioned, and interfacial space charge at heterogeneities such as grain boundaries. Well, I have mentioned just now that it is a normally electrode electrode interface acts as a accumulation center or accumulation site for the charge carriers or the charges, but if there is a inhomogeneities, for example, a grain bound in a polycrystalline material, particularly in ceramics, you have grain boundaries which is inhomogeneities, and that also creates some kind of a surface. So, when charges are moving across, trying to move across the grain boundaries, there may be an accumulation because of the imperfections of the lattice. So, in addition to the metal interface or the metal electrodes interface with the insulator or with the dielectric, within the dielectric itself there may be some inhomogeneities, and that may also act as a site for accumulation of charges, where the charges are not properly neutralized, and therefore, there will be accumulation, and that accumulation will lead to the enhancement in the dielectric moment or generation of dipoles and dipole moment. So, that is also a center where polarization can take place. So, this is the polarization mechanism, and I think we can complete it here today. The frequency dependence of different polarization mechanisms, I think we will take it up in the next lecture. Thank you so much.